Simultaneously, he's a senior fellow at the Woods Institute of the Environment, and he's going to talk here about water.
All right, thank you very much. I'll just get right into the points of the talk. The first is that supplying clean water takes lots of energy. One way that we can address this energy-water nexus problem is with new infrastructure of the type that I'll talk about in just a moment. Importantly, in the parts of the country where we live, in the parts of the country where we saw all those photovoltaics going in, the dry, arid West, in the future we'll be less dependent on imported water. That's just a given. But we can address these challenges by transforming stormwater and wastewater from liabilities into assets. So what I'll do briefly here is give two examples of these issues with regard to water and two examples with regard to wastewater. So just for context, I want to remind ourselves that in the state of California, we move water over vast distances. In the West, the major cities exist because of importing water. And I show here the California State Water Project. That's the red line that goes through the Bay Delta over the Tehachapi Mountains all the way down into Los Angeles. The other part of the water supply for Los Angeles and San Diego is the Colorado River Aqueduct, again, pumping through the Mojave Desert and over mountains. So these were the vast infrastructures built in the previous century, but this is not a path for the future. If we look at the energy that's required to supply water in our area versus Southern California, there's quite a bit of difference. It's not in wastewater treatment. It's not in water treatment. It's not in pumping the water around the cities. It's really getting the water to the cities. So what we see here is if you look at the kilowatt hours per cubic meter between Northern and Southern California, there's a factor of 3 difference. And that factor of 3 comes from the fact that to get water down into LA and San Diego, we have to pump hundreds of miles and up and over mountains. So, what do we think about this? Well, this is the energy cost for importing water. In the future, we're not going to import more water. It's very likely we're going to get less. So, let's look at the first example here. And this is the Santa Clara Valley Water District. And this is a pie chart that shows where all the water comes from. And I think the first thing you want to get from this picture, it's a pie chart. There isn't one place where that water comes from. It comes from lots of different sources. And this is part of our water future, lots of different sources. And one that I've circled here is recycling. Right now, water recycling provides about 4% of the water for the Santa Clara Valley Water District. There's a plan to more than double that. And how will this be achieved? And what will be the energy cost of doubling the amount of water that we have when we go to water recycle? Well, this is part of the future. So, this is the current situation. Imagine the cities at the top are San Jose, Milpitas, Santa Clara. They all produce wastewater that goes to a centralized facility at the south end of the bay. It's processed through a lot of treatment steps that produce water of very good quality for discharge to the bay, but you can go through a couple of other steps and produce water that's suitable for irrigation and industrial purposes. So this is water that's available for recycle. Now, one of the interesting things about this sketch is that arrows going up the screen. So one of the energy costs in this kind of picture with a centralized facility is you have to pump the water back uphill. And in the future, when we think about water recycle, one of the messages will be we'd like to do it in decentralized systems so we can capture and reuse the water at the places where it's generated and needed. But let's look at these energy costs now. Excuse the units here, it's kilowatt hours per acre foot, but just look at the height of these bars here. The one in the middle where I say current supply, that's the energy required currently for that mix of water that the Santa Clara Valley Water District provides. The one over on the far left of the screen is the energy required for recycled water. And what do we see there? Well, it's a factor of 2 difference. So this is really great. You take that water, run it through all these additional treatment steps, water that would otherwise go to the bay, you can recycle it, and it takes half the amount of energy of your current water. So, but there's one thing here, that's, there are 2 little boxes there, and one of those boxes relates to conveyance and pumping. And if we go to decentralized systems, like imagine a system here at the Stanford campus, we could cut that in half. And that's what we'd like to do someday. All right. We want to go from 4% to 10% recycled water. There's a little bit of problem here. And that's that current water is too salty right now for expanding its use. So we need to take the salts out of that recycled water. How are we going to do that? Well, you can run through a series of steps that are proven, and these would be microfiltration, reverse osmosis, UV disinfection. And that basically produces pure water. Take that pure water and then blend it with that recycled water, and the blend gives a lower salt content. But of course, this takes energy to go through those treatment steps, particularly the reverse osmosis, because they're high-pressure systems. So how does the energy picture look with this? Whoa, well, there it is. It's higher than recycled water, but still lower than the current blend. And I show you pictures here of the microfiltration, the RO systems, and the UV systems. That's what's called the Silicon Valley Advanced Water Purification Center when I took my class on a tour there in March. I want to point out one other thing, and that's that water that's produced is essentially pure water. So when I say 2/3 recycled water plus 1/3 pure water, this is water that is very close to drinkable quality. So this is a 10 million gallon a day facility, and in the future, what will likely happen is we'll get confidence with this facility, and we'll put that water into our groundwater systems or into a reservoir, and that will promote indirect potable water reuse. Something that's coming. But not do it right now, do this blend, get experience with it, get the public comfortable with the idea. Now another way to save energy is to take advantage of natural systems. Natural systems like I show wetlands here, or bioinfiltration systems along the curb here. One of the areas in which we're researching is how to bring natural systems into the urban environment in a reliable way so that they can function as part of our urban water infrastructure. And natural systems can provide enhanced water quality, urban sourced water, they can improve the urban aesthetics, and create habitat. So where might we see these systems? Well, in water reuse, and in stormwater capture, and in groundwater recharge. So let's take a look at stormwater capture. And this takes us down to LA now. There are 2 pie charts here. The one on the left shows where Los Angeles gets its water now. The one on the right shows where it will get its water in about 15 or so years. What's changed in this picture? There is one really big change. This wedge right here got a lot smaller. What is that wedge? That's the wedge from the water wholesaler, Metropolitan Water District. That's the agency that takes the water from Northern California, moves it down to Southern California, and then wholesales it. What's LA's future plan? Much less imported water from Northern California. And you'll notice that there are more pieces on this pie chart. There are more wedges there. One of the wedges I want to point to is the stormwater capture. What do we think about stormwater right now? Let's use the example in LA. Well, the one picture here is Sun Valley. That's an area north of the Burbank Airport. It floods regularly. What do we think of when we think of rivers in LA? Well, I'm someone that likes action movies, and I tell you, there are more action movies filmed in the LA River than you can imagine. What's the consequence of this? You get this localized flooding, you get these intense storms, now Mediterranean climate, intense storms in the winter, you know what they are. You get this rush of water down to the coast. We're wasting the water, but something else is happening. You're polluting your beaches. So we have an opportunity here to solve two problems at once. Capture the stormwater for water supply, capture those pollutants so we don't contaminate the beaches. And there's an article that was just in the Times last week. So that's the strategy here. How might we do this in a way that would really make a difference? And this is a project that we're working on with our colleagues in this National Science Foundation Engineering Research Center on reinventing the nation's urban water infrastructure. We're working with the LA Water and Power Department, LA Department of Public Works, watershed management, county agencies, to think about how we could capture stormwater on a pretty large scale to make a difference. And an area that we're looking at is the Strathern Pit. And really what the Strathern Pit is right now, it's a former quarry that's now just a dump for concrete and stuff like that. But we could take that site and convert that into a stormwater capture, treatment, and recharge basin. So the message I want to leave here is there's today the 50-acre pit. There's tomorrow a stormwater capture, wetland system, and park in an area, frankly, that has very few parks to begin with. So this is something that is just a win-win in all respects. But when we go down to LA and talk to the folks, there's some cautions here. And that's that stormwater isn't clean. We have urban herbicides, for example. We have runoff from streets, chemicals from tires, and that sort of thing. So we need to design these systems in ways that we're not contaminating groundwater. So we need to do a better job of learning how to design wetland systems and infiltration systems to remove such contaminants. And those contaminants that I just showed are not on the Clean Water Act list. Those are a set that are currently not regulated. So some of the ideas we're researching here is wetlands that look more like ponds, so we can take advantage of photoreactions. Think of a photodegradation reactor. And think of infiltration systems that would have geomedia of different kinds to remove the trace level of contaminants. So these are the sorts of things that we can work with in parallel with the city of Los Angeles as they think about the design of converting this 50-acre dump site into a 50-acre park. Now, let's move a little further inland. And I want to go to the wastewater now. IEUA, Inland Empire Utilities Agency. Inland Empire is Ontario and San Bernardino and those cities. I just wanted to show you this slide I got from Martha Davis. And just to point out again what their future looks like. I didn't edit this slide except put her name on it. No additional imported Delta water. That means no more water from Northern California. Increased recycled water of the kind of systems I was talking about here in Santa Clara. Stormwater capture and groundwater recharge, the example I was just showing there for LA. And all of this would then be thinking about more resilient, reliable, and environmentally friendly systems. But since we were having these talks about electricity and peak power, Inland Empire has been looking at that. And what they would like to do is to use facilities at their plant where they actually can get off the grid with respect to peak power. So that, they have this base load of electricity, they want to get off that, and how will they do it? Well, they can take the methane from digesters and run it through a fuel cell. They're out there in the desert where they have put up a wind power system. They're in that part of the country where solar works well, they've installed that. They're doing something else kind of interesting here too, and that's that they can take food waste and convert it to energy. Now, what do you do with food? What's the idea of food waste? Well, food waste is organic matter, just like wastewater has organic matter in it. And you can take that, import the food waste, and use that to enhance the production of methane from anaerobic processes. So these examples that we're looking to the future of doing things differently, this is, I guess I would say that Inland Empire is probably the most advanced in looking at different sources of energy here and doing a good job at that. But I'd like to talk a little bit about the food waste and how we might think about that in terms of our wastewater treatment. And that'll take me to my fourth example here. This pie chart shows the chemical energy that's embodied in wastewater. Now, wastewater has ammonia, and it has dissolved and particulate organic matter. Basically, think of it as carbohydrates and protein. That wastewater has the equivalent of about 2 kilowatt hours per cubic meter. It only takes about 1/3 that to treat wastewater. Only takes 1/3. Nowadays, we don't use the systems that would fully capture that energy. In fact, we have to put energy into wastewater treatment. But we have the opportunity in the future of doing things really different. And one way of doing things really different is to forget the current technologies that we have and go to completely biological, anaerobic systems. In other words, the idea would be to take all of that organic matter and convert it to methane. And forget the current systems we do now where we add a lot of oxygen, it takes a lot of energy. And also there's some novel ways we've been working with to look at how we can capture the energy that's potentially available in ammonia as well. So what's this look like here? What could be the future treatment? We could be completely energy positive. You take the wastewater that has that 2 kilowatt hours per cubic meter of potential energy in it, use that in new and different ways, like with compact membrane bioreactors that are anaerobic, that can take all that waste, convert it to methane. You have a small amount of biosolids left over to handle. It's a really efficient system. We'd like to demonstrate this someday on the Stanford campus. 2 things we'd like to demonstrate on the Stanford campus. Energy positive wastewater treatment and distributed treatment to reclaim wastewater so that we can reuse it for irrigation and industrial purposes. Right here in the Stanford campus, meet our future energy needs, and our water needs, excuse me, in ways that are energy positive and take advantage of our own local water and not ask for more imported water. First, we're not going to get it. So we have to do something like that. All right, now, this idea of the food waste, this is pretty interesting. This is a slide I got from East Bay Municipal Utility District, and it says, Winery Waste Management Program. Well, East Bay Municipal Utility District, when you go across the Bay Bridge, like you're going to Berkeley or Oakland, you know, you over there by the toll gates, you don't pay when you go that direction. That's that whole facility there on the right. Well, what do they have to do with wine? Well, they can take the waste from winemaking, they can take the waste from food production in the Central Valley, truck it into their facility, put it in anaerobic digesters where they have excess capacity, make a lot of methane, and generate electricity. And that's what they're doing there. So, this is the last example I wanted to show. And what happened in 2012 is East Bay Municipal Utility District became the first wastewater treatment plant in the US to produce more renewable energy on site than is needed to run the plant. So, where does this leave us then? I have a lot of dots here. I guess I'm connecting the dots of sorts. Think of these as water dots, I guess. Future trends. What do we need to be prepared for? Or what do we see happening in the future? Less imported water. What's happening here? Climate change means less runoff, less water in the West. Population growth means greater demand for water. We can't take all the water and use it for cities and agriculture. We have to leave water for ecosystems. We haven't done a good job of that in the past. We'll do more of that in the future. All that means there's going to be less imported water. We're going to go to decentralized systems so that we can capture and reuse water where it's generated and needed, like here in the Stanford campus. Think about wastewater treatment as energy recovery centers, and then go to this process of indirect potable reuse. That would be, look at that system I showed down at the Silicon Valley Advanced Water Purification Facility. Basically, that's producing drinking water. In time, as we gain confidence with that kind of system, that water could go into the ground or into Lexington Reservoir or something like that. So it would be kind of an indirect potable reuse. And then also this integration of natural and engineered systems to benefit both ecosystems and urban aesthetics. So those are the messages I wanted to give. I wanted to paint a picture of where we are today and a little vision for the future, and I thank you for your attention. I got a 2. I guess that means 2 questions. There's one right here if you could shout.
This guy has the microphone in the back. And then
or maybe there's one over here with the microphone.
I just was going to make a quick comment, but in Palo Alto, when we've been working on anaerobic digestion and also recycled water, one of the things that I've observed is the lack of, if you will, environmental literacy, because there's so much fear about contamination coming back in, and as you look to do recycled wastewater and the use of gray water, a lot of times these programs are not adopted by the policymakers because the public is scared. So somehow I would think we need to teach about this approach so that when it comes up into a policy debate, they aren't ruled out because of fear of...
Right. So the question is about public acceptance of these. When we take wastewater and treat it highly through these additional steps, we comply with state standards called Title 22, and that water goes into a special pipe, a purple pipe. And you may have seen these around. So we have lots of experience with reuse of wastewater for irrigation, even on a massive scale down around in the Monterey and Watsonville area. So I think there's some comfort there. What there's not comfort with is this highly treated wastewater coming back into our public supply. So a little bit of subtext on this message then about this 10 million gallons a day of this, what I call essentially pure water. We're not going to do anything soon with that except keep blending it into the current recycled water stream. Get experience with running that plant for a long period of time. Give public tours. Gain confidence in its operation and reliability. And then later, somewhere down the road, maybe it's 10 years or so, you know, there might be another little subtle message like, you know, this water is so pure and this plant's been operating so well, maybe we could put this water in the ground or put it in a reservoir or somewhere like that. We don't necessarily have to put it back in the purple pipe system. So in other words, gain experience and comfort with it. This is being demonstrated, right now they do this down in Orange County. I didn't show those slides, but it's new here. It's not new in Orange County. But it's like a lot of things. You say, well, I want to demonstrate that it works here and gain the comfort here.
From the student in the back.
Harvesting the energy from the wastewater, I think, is a great idea. I was interested in the actual thermodynamics of the 2 kilowatt hours of energy per meter cubed in the wastewater, and then the third of a kilowatt hour in the treatment of the water. Is that from a first law perspective or a second law perspective? Because surely there's going to be exergetic losses in conversion of chemical potential to the electrical energy required to purify the energy.
Well, basically what it is you can look at the energy that's available there from combustion and then make some assumptions about what is the electrical equivalent of that. So it's, that's the potential that's there. The point is that it's about 3 times what's really needed to treat wastewater. And so even if you go through lots of processes to anaerobic processes, include all the inefficiencies and different things, you can still be energy positive. And I had to shorten my talk a little bit, so I wasn't able to show Perry McCarty's paper here that has the schematic about how all that works. Perry was just a little too busy, so I didn't show that. But the current situation is that we spend about 0.6 or 0.7 kilowatt hours per cubic meter to treat the water. So you can see we currently, we're kind of like 0.6 on the deficit. We'd go the new way, you're going to be 0.7 or something on the positive. Yeah. Okay.
Very good. Thank you, Dick. I think that's all we have time for.